now what I am going to do is in order to be able to calculate the specific heats of a free electron gas, I am going to get an expression for the density of states at the Fermi level. So, to get the density of states at the Fermi level, it is pretty easy. So, what we have from the previous lecture is that Kf is equal to 3 pi squared n to the power 1/3, or I can also write it as 3 pi squared n by V to the power 1/3. So, I have Ef is equal to h cross squared Kf squared by 2m, and that is equal to h cross squared by 2m into 3 pi squared n by V to the power 2 by 3. Now, since we have an expression for Ef, what I can do is I can write down Ef to the power 3 by 2, and I want to get an expression for the number n. Okay. So, to get an expression for the number n, what I will do is I will take Ef to the power 3 by 2 is equal to h cross squared by 2m to the power 3 by 2 into 3 pi squared n by V, or I can get the expression for n as equal to V times 2m by h cross squared to the power minus 3 by 2 times 3 pi squared times Ef to the power 3 by 2. Now, I can take logarithm on both sides, so that I have log n is equal to log of the constant, which is actually the constant is this part, and plus 3 by 2 log Ef. So, now I can differentiate this with respect to n and E, in which case I will get dn by n is equal to some 0 plus 3 by 2 def by is not def, it is just de, because I am differentiating with respect to energy. So, because of this I can write down dn by de is equal to 3 by 2 n by Ef, and this is nothing but the density of states at the Fermi level. So, very simple expression for the density of states at the Fermi level. Now, let us after having obtained all the basic quantities like the Fermi velocity, the density of states at the Fermi level, and many of those properties of the free electron gas, what I will do is I will try to go over to calculating the specific heat. So, to calculate the specific heat, one can actually do a back of the envelope kind of a calculation, where what we will do is we will plot density of states as a function of energy. So, this one is a e to the power half dependence. So, it will go like this, and if the Fermi energy is somewhere here, then I will have, so this is the Fermi energy. At a finite temperature, what happens is that the energy at a temperature T, the thermal energy is kBT. So, the only electrons that can get excited are those which are within kBt of EF. So for example, so what will happen is the density of states at finite temperature will look like the occupied states will be looking like this. And this energy is kBt. So you can only excite electrons which are within about kBt of the Fermi energy. The others you cannot excite because the excited states are already occupied. For example, if you take an electron somewhere here and try to excite it, so if you want to, you only can excite by an amount kBt, but this state is occupied. Okay, so you cannot excite from here to here. This excitation is not allowed. So you can only excite electrons which are near the Fermi level within an energy range of kBt. So that means that the classical expression for the specific heat C classical is 3/2 kB, where we have assumed that every one of the electrons it's possible to excite every one of the electrons because there is no Fermi the Pauli exclusion principle or the Fermi Dirac distribution. So any state can be occupied by any number of electrons in a classical case, and so it is just 3/2 kB. So when I go to a Fermi gas, number of electrons that can be excited is the fraction kBt by EF. So C classical will get reduced. So C Fermi, for a Fermi gas, C will be equal to C classical times kBt by EF, or is equal to C classical into T by Tf. So for the Fermi gas, I can write down CFG is equal to 3/2 kB into T by Tf. Now let us see whether this result really holds up when we do a more exact calculation. It is a very simple calculation to do. So for that, what we are going to do is, first of all, find the energy difference delta E at a finite temperature T and at 0 temperature. So delta E is equal to energy at a finite temperature, which is given by energy of the states, density of states at that energy, times the probability of those states being occupied, times dE, minus, and this goes all the way from energy, the variable goes all the way from 0 to infinity, the integration variable, and you have to subtract from this the ground state energy or the energy at t equal to 0 k, which means that you are only going to go from 0 to epsilon f, which is the Fermi energy, epsilon d epsilon d of E. Well, we will do a slight trick in this case. So what we will do is we will take the number of electrons in the system is simply given by integral 0 to infinity f of E, which is the Fermi Dirac distribution function, times the density of states d of E times dE. I can write down what is epsilon Fn, which is equal to integral 0 to infinity. I will take epsilon f inside even though it is a constant, f of e d of e d. Now I have two equations, one corresponding to delta E and the other corresponding to E of n. If I differentiate the first equation with respect to T, then what I will get is a specific heat. So, d delta E by delta T is equal to specific heat is equal to integral 0 to infinity epsilon d epsilon. These are actually just constants for the given system, so they do not depend upon temperature. The only thing that depends upon the temperature here is f of E. So, I have d f of E upon dt times dE, and of course in the second term there is no temperature dependent factors at all, because the energies of the eigenstates are not temperature dependent and neither is the density of states temperature dependent. So, that goes to 0. The second expression also goes to the, if I differentiate the second one, even that is going to give me a 0 equal to, let me say, d epsilon f n by del t, and that is equal to integral 0 to infinity epsilon f d of E del f epsilon by del E d. Now, if I subtract 0 from CV, it remains the same. So, I can subtract equations 3 and 4. So, I subtract equation 4 from equation 3, and what I will get is CV is equal to integral 0 to infinity epsilon minus epsilon f d of E del f E by del E d epsilon. Now we can find out the expression for del f E by del E, because we know what is f of E. F of epsilon is equal to 1 upon e to the power epsilon minus epsilon f divided by kBt plus 1. So, I can do a differentiation of function. So, I get del f E by del E is equal to minus 1 divided by e to the epsilon minus epsilon f by kBt plus 1 squared multiplied by e to the minus epsilon f by kBt multiplied by minus epsilon minus epsilon f by kB t squared, or this just gives me e to the minus epsilon minus epsilon f by kB t divided by e to the power epsilon minus epsilon f by kB t plus 1 the whole squared into epsilon minus epsilon f by kB t squared. So, once we have this, we can actually substitute this into the expression for CV. So, CV will now be given by C Fermi gas will now be given by integral I will just come to that one, integral 0 to infinity epsilon d epsilon epsilon minus epsilon f by kB t squared. There will be a square term here because I have an epsilon minus epsilon f to begin with, and I have e to the minus epsilon minus epsilon f by kbt divided by epsilon e to the power epsilon minus epsilon f by kbt plus 1 the whole square times d epsilon. Now the important thing is the following, that is df by de is a sharply peaked function at EF, because as you see from the distribution function, it is actually a step function at t equal to 0 and not very much spread out when you are t is closer to Tf. Say for example, see, you can see here already that it is a really sharp step function at EF at t equal to 0 and is quite sharply dropping d of E even at finite temperature, as long as the temperatures are small enough, and we are looking at t by Tf of the order of 10 to the minus 2 or 10 to the minus 3, and so because of that even this function is going to be very sharply peaked. So which means that the contribution that we are going to be having, which means that d of E can be taken as a constant as at d of EF. Okay, so I can write down C Fermi gas as equal to d of EF times kb squared times integral 0 to infinity d epsilon epsilon minus epsilon f the whole squared divided by kbt squared times e to the epsilon minus epsilon f by kbt divided by e to the epsilon minus epsilon f by kbt plus 1 the whole squared. So this is the integral that I am looking at. What I will do for actually solving this is I will change the variables and say that x equal to epsilon minus epsilon f by kbt. So I have dx epsilon f epsilon by kbt. So d upon kbt. So dx is equal to d upon kbt, and the variables of integration are when x is equal to 0, when epsilon is equal to 0, x is equal to minus epsilon f by kbt, and when epsilon is equal to infinity, x is equal to infinity. So on making this change of variables, then what we will have is the following, that is C Fermi gas would be equal to integral minus epsilon f by kbt to infinity minus epsilon f times I will take epsilon f kb times x squared I have d of EF here, okay, times e to the x divided by e to the power x plus 1 the whole squared times dx, which is kbt right, because dE is equal to kBT times dx. So this will be C Fermi gas is equal to kB squared T times dEf times integral minus epsilon f by kBT to infinity x squared e to the power x divided by e to the power x plus 1 the whole squared dx. Because EF is far larger than kBT, integrand is small for values of x less than minus epsilon f by kBT. Because it goes as e to the minus epsilon f by kBT, so e to the minus epsilon f by kBT keeps reducing as the value of minus epsilon f by kBT becomes smaller and smaller, more and more negative. Okay, so I can actually replace minus epsilon f by kBT by minus infinity. So I will have C Fermi gas is equal to kB squared T dEf times integral minus infinity to infinity x squared e to the power x divided by e to the power x plus 1 the whole squared dx. And this integral can be looked up in the table of integrations, table of integrals for definite integrals, and what you get is this integral gives you the value pi squared by 3. So I have CFG is equal to kB squared T divided by 3 into pi squared into dEf. Now we have already obtained an expression for the density of states at the Fermi level. The expression for density of states at the Fermi level is (3n) divided by 2 kBTF. So I get C Fermi gas is equal to 1/2 kB times pi squared by 3 into 3n. So 3 will go, kB squared T that I had, so I will have a T in the numerator, and in the denominator I have kB TF, where I have used the expression that EF is equal to kBTF. And so the specific heat per electron is given by CFG by N is equal to C Fermi gas per electron is equal to 1/2 pi squared into T by TF. I think I have a missed factor of 2, just 1 second. Pi squared by 3 kB squared T by 3. So I have kB squared T by 3, so I must have a kB here. So this kB goes against so 1 kB goes with kBT. So I have kB and pi squared by 3, and d of EF is 3 by 2. So I have a 3 by 2, so I had a 2 here, so it's okay, 1/2 pi squared kb T by Tf. So this is how we can get, in case I have missed a factor here or there, please get back to me and we can correct it, okay. So what we have got is an expression for the specific heat. Specific heat of a Fermi gas. Now what is interesting is that this specific heat is smaller by a factor of T by Tf compared to the classical. So C Fermi gas goes as C classical times T by Tf, and T by Tf is typically of the order of 0.01. So the classical specific heat is greater than quantum mechanical specific heat by a factor of 10 to the 2. Okay, and the classical velocity is less than about quantum mechanical velocity by 10 to the minus 2. So wherever we got the ratio of a product of specific heat into velocity, like in the case of the Lorentz number that we calculated, or the Wiedemann-Francis law, we saw that there was a cancellation of the error which was created by overestimating the specific heat and underestimating the velocity. So quantum mechanical Fermi gas actually calculation fixes it correctly, and we also see that the mean free path is much larger, okay. And so the mean free path is much larger in the sense that I have the velocity which goes as something like 10 to the power 7 to 10 to the power 8 centimeters per second, and I have a tau which is of the order of about 10 to the power minus 14 seconds. Ten to the power 7 to 10 to the power 8, and so V tau is equal to mean free path is roughly about 10 to the minus 6 centimeters, or about 100 angstroms. And we also see that it correctly gives the thermal conductivity, because as we saw, the thermal conductivity was overestimated by the classical free electron gas, but quantum free electron gas, the thermal conductivity is much smaller, because you see that the mean free path is much larger. Okay, so what I am going to do is I will stop at this point, and in the next lecture I will discuss the shortfalls of the free electron gas calculations and how we can go beyond free electron theory, and we will then come to nearly free electron models, and further to that some energy band calculations. Thank you very much.